We usually think of numbers as just points on a line, right? Stretching out forever in both directions. But what if that's only half the picture? What if there's this whole other hidden geometry tucked away inside the numbers we use every day? Well, today we're going to pull back the curtain on that.
I mean, seriously, what if something as simple as multiplication wasn't just about crunching numbers? What if it was actually a geometric move? Like a rotation or a stretch, or even a beautiful spiral. It sounds kind of wild, right? Well, let's dive in and see for ourselves.
Okay, so we've all got the number line down. It's comfortable, it's familiar, it's home to every real number you can imagine. But then you run into this one weird little number, the square root of -1, I. And suddenly, there's a problem. It just doesn't fit. There's literally no room for it on the line. So where in the world does it go? Well, to find it, we have to do something radical. We have to go off the line and into a whole new dimension. All right, so we're making the leap from a one-dimensional line to a full two-dimensional plane. And trust me, this is where numbers really start to show their true colors and their hidden shapes.
And here it is, the complex plane. Think of it like a giant map for numbers. The horizontal line is for all the real numbers we already know. And that new vertical line, that's for the imaginary numbers. So now, every single complex number, which is just a mix of a real part and an imaginary part, gets its own unique home. For example, the number 2 plus I, you just go 2 units to the right on the real axis and 1 unit up on the imaginary axis. Boom, there it is. And just like that, these abstract ideas become real, tangible points in space. Now, what's really cool is that on this plane, addition suddenly makes perfect visual sense. If you think of each number as an arrow pointing from the center, adding 2 of them together is as easy as playing connect the dots to form a parallelogram. The answer is just the diagonal. It's clean, it's simple, it's totally intuitive. But multiplication? Oh, multiplication is a whole different beast. That's where the real puzzle starts. So, we've got addition figured out. Now let's tackle this algebraic puzzle that is multiplication.
Okay, so here's the official by-the-book rule for multiplying two complex numbers. And look, it works. It gives you the right answer every single time. But just look at it. It's a total jumble of symbols, right? Unlike that elegant parallelogram for addition, this formula gives us 0 clues about what's actually happening geometrically. It's just algebra soup.
And that brings us to the big question. What does this mess of a formula actually look like in action? When we take 2 points on our plane and multiply them, where does the new point land? And more importantly, why does it land there? I promise you, that jumbled formula is hiding a secret, and it's a surprisingly beautiful one. So let's look for our first clue. What happens if we just keep multiplying by I over and over? Okay, let's start at the number 1. We multiply by I and we land on I. Makes sense. We do it again. I squared is -1. Do it a third time, we get -I. And one more time brings us right back to where we started, at 1. Did you see that? Each multiplication was a perfect 90-degree turn to the left. This is huge. This is our first real hint that multiplication has something to do with rotation.
Okay, so this whole rotation thing is a massive clue. It suggests that our usual way of thinking, how far over and how far up with x and y coordinates, might actually be getting in the way. To really understand rotation, we need to look at these numbers from a totally different angle. We need a new perspective.
So, instead of the old x and y game, let's try something new. Let's describe every point using 2 different things. How far is it from the center, and what angle is it pointing at? This is what we call polar coordinates, and it's all about distance and direction. First up is the distance, r. In math speak, this has a fancy name, the modulus. But really, all it is the length of the number, how far it is from the origin. And you can find it super easily with the good old Pythagorean theorem.
And the second piece is the angle, which we call theta, or the argument. That just tells us the number's direction. So you've got length and direction, modulus and argument. Together, they can pinpoint any number on the plane. But now we have a new problem. How do we connect these geometric ideas back to the algebra of it all? Well, that connection comes from what is, hands down, one of the most beautiful and mind-blowing formulas in all of mathematics. This is it. This is the secret key that's going to unlock this whole puzzle for us. Behold, Euler's formula. Now, what this does is nothing short of magic. It creates this incredible bridge between the number e, imaginary numbers, and trigonometry. Since cosine and sine are all about points on a circle, what this formula is really telling us is that raising e to an imaginary power is the very definition of pure rotation. It's just spinning around in a circle.
So if we put all of that together, it means we can now write any complex number z in a brand new way. Forget x plus iy. Now we can write it as its length r times e to the power of I times its angle theta. This new way of writing things, this polar form, is about to change the entire game. Okay, we've got our new tool. We're armed with this powerful exponential form. So let's go back to that messy multiplication problem and see if we can finally crack it open. All right, let's take two complex numbers, but this time written in their new polar form. Now, when we multiply them, watch this. All that horrible messing algebra from before, it just disappears. All we have to do is use the simple rules for exponents we all learned back in high school. You just multiply the lengths together and you add the exponents. And there it is, the hidden geometry, right there in plain sight. To multiply two complex numbers, all you do is multiply their lengths and add their angles. That's it. That ridiculously complicated formula was just a disguised way of saying scale and rotate. It's so simple and so elegant. So now that we've cracked the code, we can see that complex numbers are so much more than just an algebraic curiosity. They're actually a language, a powerful language for describing geometry. Yeah, this new perspective gives us this amazing algebraic toolkit for moving things around. Basic arithmetic suddenly has these incredible geometric powers. Adding a number, that just slides a shape across the plane. Multiplying by a number whose length is 1, that's pure rotation. Multiplying by a simple real number, that just scales it up or down. And multiplying by any other complex number, well, that does both at once. It creates a beautiful, perfect spiral. It's this incredibly compact and elegant language for describing transformations. So think about what we just did. Just by adding one extra dimension to our boring old number line, we discovered that the simple act of multiplication was secretly a geometric spiral all along. And this beautiful connection between algebra and geometry, it's not just some cool party trick. It's the bedrock of entire fields, like electrical engineering and quantum physics. It really makes you stop and wonder, right? What other amazing, elegant secrets are just waiting to be discovered, hidden inside the things we think we already know?